So this is a research paper that caught my eye for a few different reasons. The main reason why it caught my eye is that if you've done anything at all with regards towards reinforcement learning, then you have stumbled upon and asked yourself these same exact questions that they're asking within this particular research paper. The research paper is called Rethinking the Foundations for Continual Reinforcement Learning, and it's put out by the University of Alberta. And then, so diving into this very specifically and starting off, there's a difference between reinforcement learning and continual reinforcement learning. So we'll define reinforcement learning as learning from an environment during a training process, whereas continual reinforcement learning would be learning from your environment on a continual basis. So we'll frame those as two separate and competing problems in this instance, because to me and to the authors of this paper, they aren't the same goal, and we aren't tracking towards the same goal overall, is kind of the point that this research paper makes. So they suggest that there's essentially four frameworks or four foundations to modern reinforcement learning. And then their assumption, their argument is that we should look at these four foundations and then decide whether or not they actually fit within the realm of continual reinforcement learning or not. So the four foundations are the Markov Decision Process formalism, a focus on optimal policies, the expected sum of rewards as the primary evaluation metric, and episodic benchmark environments that embrace the other three foundations. So diving into that, it's a short research paper overall, but that's kind of what they dive into, is these four claims, right? So these four foundations. And then the appropriate mathematical formalism is the Markov decision process. We often presume additional properties of the MDP, such as finite space and action spaces or compact spaces with continuity assumptions. Furthermore, we typically make ergodicity assumptions, such as the MDP being unichain or communicating. The bottom line here is essentially the MDP chain in of itself is question number one, right? Should we actually be utilizing the Markov decision process for these things? And then secondarily, the way that we're utilizing the Markov decision process in these instances doesn't actually model the real world, right? Like, the real world is not a video game where you have very distinct start and end, and then it's episodic, is the way that we train AI models on video games overall, is the process that they note within this. And then highlighting essentially the bottom line, a lot of people question what's the difference between Bayesian networks and Markov decision processes. So if we weren't to go with Markov decision processes, what would we likely go with? The likely alternative to that would be Bayesian networks. Bayesian networks are and Markov decision processes, MDP, are both stochastic methods. So they're both probabilistic methods, right? And they're both probabilistic graph-based methods, and they're both graph formalisms. And then so a Markov process is any stochastic process that satisfies the Markov property. So it's just like a mathematical situation and an example. Within a Bayesian network, therefore you can represent a Markov process within the big thing that I want to mention within this, and why I'm highlighting and pointing out this discussion here, is that a lot of people don't understand and don't know within this that you can actually model Markov decision processes, or MDP, utilizing Bayesian networks. I've done a lot, and I've showcased a lot on my channel. Every so often, right, I'll play around with Bayesian networks, Bayesian probability networks, and then essentially Bayesian networks are pure probability chains, right? And Markov processes are pure linear chains. And that's kind of the bigger difference there. But it's important to note that you can model Bayesian networks as a linear chain indexed by time, which is the hallmark of an MDP process, right? And then so why I bring that up is that you don't need MDP processes 100% in order to get the effects of MDP, but the authors of this paper are right. Every single RL algorithm that I've ever seen is MDP based, when it could be Bayesian based, or it could be something else based, right? if I was to think about this 100% purely philosophically, it's my philosophical assumption that the way that our brains work in these instances, and that it navigates environments, is neither a Markov-based algorithm nor a Bayesian-based algorithm. I think that there's something within that we're still missing. And then so by having these discussions and then looking at things from different angles, we can at least get closer towards that ground truth, and then recognize that perhaps both of the main algorithms that we have in this particular instance, or the multitude of algorithms that we have in this particular instance, aren't actually like shooting towards the right goal overall. And then so the second aspect that they mention is the goal of reinforcement learning algorithms is to produce artifacts. And then so artifacts here means any atemporal representation of an agent's learned knowledge, such as policies, value functions, options, or features. We often give considerable concern to the notion of optimal value functions and optimal policies. We think of algorithms having a training period wherein they aim to converge to optimal artifacts and follow that with a testing phase to evaluate the general artifacts. This foundation is also notably critiqued as a dogma 2. And then that's, I think, a very significant and important critique within this, and highlight within this overall, right? That's the main flaw and drawback of our goal with reinforcement learning algorithms at the moment, is that they I talk about abstractions a lot on this channel, right? So it's abstractions of data, abstractions of an environment, abstractions of a video game in this instance, when we're taking like very simplistic and simplified examples of that. And then so you're creating like an abstraction of the dogma of the abstraction, so dogma 2. And then so it's kind of like a weird place to train models in, right? Like, is that actually like, is there an actual environmental interaction within that? Because it's all abstractions of abstractions, right? And then so like, what's the real world like significance, and how does that play into that in real world terms, is kind of like the question that they ask here, that you should ask yourself here. And then so the next one is, the ideal measure of evaluation is the expected sum of rewards, possibly discounted. In episodic environments, this is the episodic return, and we desire that during training. We see the episodic return approach the return of the optimal policy. Episodes allow one to draw IID samples of this return for any stationary policy, which is often how evaluation is performed during the testing phase. And then so if you're not familiar with this overall, like, this is to me, the biggest argument against reinforcement learning overall. And it's a big problem that I with it, very honestly, every time I play around with it, right? And it's like, is this actually learning? Like, what is actually going on here? And then so what we're looking at here is reward charts. So we're looking at the reward function for different games that a model is trained on, right? And these are Atari games, just like Cubert, River Raid, Space Invaders, Mario, Pong, Montezuma's Revenge, Breakout, and Beam Rider. And then, but what you can see is, so like these are like up and down, right? Like, let's look at Breakout as a good example, and then look at the yellow in Breakout, and then see how it just is like shooting up and shooting down, and like there's no like any sort of like convergence to this overall, to me, right? And then this is what happens when you train the model for like, let's say like 6 hours on Breakout. This is what your chart will look like at the end, and it's like major dips and highs and it peaks. So it's like you'll think like right around like, you know, that first third, that like, oh, okay, it's learning, right? Like, it's actually doing stuff, and then all of a sudden you'll just hit that, like it'll just hit the floor, and it's like it goes back to like 0, and it's like, what is going on here? And then you can see it climbs back up, and then it like sometimes like even there towards the end, right, it'll like hit like towards 0 again. And it's like, dude, like you've been training for like 5 hours, and then like you go and you do like the same mistakes that you made 5 hours ago. Like, what's going on? And then like it's all based off of the reward, right? And then but within that, like, that you'll get the same reward number 5 hours later. And then so like, is that actually learning? Like, we should be evaluating and questioning these things, right? I question these things every single time I train a model on these things. These are the questions that come up in my head. And this paper is just, you know, highlighting, like, we should think about this. Like, is there our current, are all of the assumptions that we're making within our current reinforcement learning process the actual answer? Do these things actually matter within it? And then the last thing that they say is that most benchmarks for comparing reinforcement learning algorithms are episodic environments. environments. So common environments such as classical control tasks and the arcade learning environment, or AL, which is how you play like the Atari games, are episodic, making them communicating MDPs. Other naturally continuing environments such as Majuko and Minecraft are often truncated during training, converting them into basically episodic tasks. A few examples of continuing never-ending environments such as the Jelly Bean World exist, but have not been widely adopted. And then so kind of the bottom line within this, and this is like 100% true, right? Even within studies that I see where they utilize Minecraft, it's always towards like tool crafting and tool usage, and then there's like the big goal. They put a reward function of the like models, and I know that I don't play Minecraft at all, right? But I know it's like a mine diamond or create diamond, like. I think it's Mine Diamond, and again, I've never played Minecraft in my life, right? And I know that just purely because I know that that's the reward function for training a model on Minecraft, is that like you train it to be able to mine. If it can mine diamond, then it's like it's gravy, right? But so within that, you're narrowing the environment. You're creating an episodic linear process for it to follow, right? And that's the argument that they make here. And then so within like any video game that you do, and like I think it's cool to look at the this chart that we're looking at here, like Qbert especially, right? Because Qbert is a game that like it starts over and over again, and then you can see how that breaks down within this, right? Like to me, when you look at the and you watch a model like reinforcement learning play Qbert for hours on end, like you'll question like is it actually learning? Like is it actually learning from the environment, right? Because it's like Qbert to me is, out of all of these games, one of the ones where it's not like the most non-linear stuff gets put into it, because like every single time that you restart that game, it's like the starting outcome and starting sequences could be different, right? Because it reshuffles how the game board essentially operates overall, and the starting game board. So it gives you a different example based off of and compared it to the linear environments that we typically do, and like this is like not a good training loop here, right? Like the model's not learning much from this, and it's very up and down, very sporadic, right? And I noticed that via this Qbert model, because I've trained models on Qbert, and like these are the same things, right? And this paper stuck out to me because I have these questions. Like every single time I've trained a model on Qbert, I've questioned exactly what this paper is talking about. And then so if you have like hands-on experience with these things, surely you've questioned these same types of things, and that's all that this paper is highlighting, right? It doesn't present like here's what should be and what could typically potentially replace our current processes. I bring up one example, right, of like, so they bring up like questioning MDPs, and then so the example that like what we could do and what that opens up for is like looking into further research via Bayesian networks, right? Which is like what I try to do a lot on this channel whenever I can. But highlighting those types of things overall, right? It's just a matter of like just questioning our assumptions. Like there's no problem with questioning assumptions, questioning why things work, questioning how they work overall, right? That's kind of how we progress things overall, rather than just like, this is the way it is and this is how it does. Like why? I mean, this is how it is, and this is what it does for like Qbert, but like why does it do that? Like, you know, that's kind of the bigger questions overall that I have within this. And then so just highlighting that and pointing these things out overall, and then like why does Mario operate differently than any of these other ones when you're looking at those two? Like I have questions about these things, right? Overall, is this actually learning? I don't know. Like I can't say like definitively that any of this is actually learning off of these charts. Like I would say I would lean towards it not learning based off of these charts, but I would also say that that's probably a flaw within our current understanding of reinforcement learning, exactly what this paper is saying, and that we should be looking into, right? And so when I actually take the step of questioning my assumptions, I think that this research paper has a lot of legitimacy within it, which is why I bring it up. Hopefully you've enjoyed it. I'll leave a link to the research paper. If you like this type of content, please like and subscribe. Thank you very much.